Hi, everyone. So, this next lesson is kind of taking everything that we have been talking about with first and second derivatives and talking about how they show up on a graph. So, we you should have this table in your notes. And I do have a copy of this posted. So, if you need to get the table filled in, there's nothing really new here. It's just pulling together, like, for example, critical points are when the first derivative is zero. And we want to talk about how do these things show up on a graph. So, I mentioned when we filled out the table that these questions that you're going to be asked, a lot of the times, this is where they're starting you. They're starting you with f prime and then asking you questions about the concavity and the increasing, decreasing, and things like that. So we really want to focus on f prime and how f prime relates to both of these things. And remember that the questions we're answering are about what is happening with f, but we're looking at f prime. Okay? So, like, as an example, your critical points are when f prime equals 0. So, on the derivative graph, those are going to be here, right? Those are your critical points. And you should notice that if you track those upward, so for example, if I were to draw this line straight up, that corresponds to a minimum value or a maximum value on the original function. So like this critical point corresponds with this point here. This critical point corresponds with this kind of dip right here, and this one corresponds with that maximum. Okay. I can also talk about whether those critical points are mins or maxes depending on how the derivative is changing. So this one is a derivative that's changing from positive to negative, okay? Which means that this is a maximum value because my function went from increasing to decreasing, okay? This one, the derivative is changing from negative to positive. And so negative to positive would correspond with a minimum value, right? So this is a max. This is a min. I'm not going to fill in all of them just for the sake of your time. But those are the things that we should be able to tell. Okay. The other thing that I can tell by looking at that first derivative graph is the concavity. So, for example, when the derivative is decreasing, right? All of this is decreasing. That's where I'm expecting to see this concave down happening on my original function because that's when my second derivative is negative, right? So this spot right here corresponds with where my second derivative is negative, okay, or where it changes from negative to positive. And all of that corresponds with the fact that this is concave down, okay? This then, that minimum value on my derivative graph, that corresponds with an inflection point, okay? Because that corresponds with when my second derivative is 0, right? And if I head upwards with that, sorry, this is really hard to draw this line going upward. This point right here would be that place where my concavity is shifting, right? This is concave down, but this would be considered concave up. And this is where that's changing, and that corresponds with this as an inflection point, okay? And I could do the same thing. I could say that this portion of my derivative graph is increasing all the way to this maximum value, okay? And this part where we're increasing corresponds with this whole portion of the graph that's concave up. This maximum value here, this place where that shifts, corresponds with this 0 on my second derivative graph. That's your inflection point. This is your inflection point. And if I head up here with this one, this is my inflection point. Okay? So you can see how those things show up on all of the graphs as you sort of look at them, but this is always where you're starting. This is always what you're looking at first. Okay, so let's do some examples of that. This first example does exactly what we just said. It gives you a graph of f prime. And let me get this zoomed in just a little bit. I'm using kind of an older document camera here, so the zooming doesn't always work the way I want it to. Okay, so the x-coordinates of any relative maxima on the graph of f, and I cannot remind you enough that this, what we're looking at, is f prime, right? So relative maxima, we know these are going to happen at critical points, okay? And a special type of critical point, but let's just start by identifying those. Critical points are when f prime is 0, okay? So I'm looking for when does f prime equal 0? That would be here and here. It technically happens at the end, but we don't typically consider endpoints to be critical points. Some mathematicians do. I don't want you to stress about that. So let's just worry about these 2 points. These are what we know are our critical points. Now, in order to be a maxima, it can't just be a critical point. We need that derivative to be changing from positive to negative, right? So if I look at this, here my derivative is positive. Here my derivative is negative. For this critical point, I've got a negative derivative and then a positive derivative. So this one, this critical point, is where my derivative is changing from positive to negative. So I would say I have a relative maxima at x equals -1 because f prime changes. I'm justifying this the same way we did analytically, right? From positive to negative. This, by the way, would be a minima, right? This is a minimum value because f prime changes from negative to positive. So this would be a decrease to increase. Okay, inflection points. Inflection points are going to be places where we have a change in direction. Now I'm going to be a little bit pickier when we write our justification here. But essentially what we're looking for are maxes and mins on our derivative graph. Okay, so on our derivative graph, f prime is decreasing, and then here f prime is increasing. Okay, so this right here represents an inflection point. Also, this right here represents an inflection point. The places where you're changing from increase to decrease or decrease to increase. Okay, so I would say that my inflection points are at x equals 0 and x equals 2 because f prime changes from increase to decrease or decrease to increase. Now, that answer right there is what I'm hoping to see from you. It's a little bit nitpicky right now because I bet some of you are thinking, why couldn't we just say it changes direction, right? That would be shorter. And right now, I feel like if you say change direction, I know what you mean, and I'm really happy that you know that that's where the inflection point is. And like I hate to be this nitpicky, but I also don't want to teach it to you wrong. Okay. The problem with this change direction thing is you don't always have to have an inflection point with just a change in direction. And let me show you what I mean by that. If we had a graph, actually, let me just go down here. If you had a graph that did something like this and then something like this, okay? This right here is technically a change in direction. We were going this way and now we're going this way, okay? But that's not an inflection point because this graph continues to be increasing. So the concavity never changed. So just saying change in direction is not quite good enough, okay? We want to establish that like the actual like increase versus decrease is what changed. So this is what you should be justifying your points of inflection with every time. Okay. When is f concave up? Well, remember we want to think about what is f prime doing when our function is concave up. And I'll remind you about this table here. When we're concave up, f prime is increasing, right? Because then you have a second derivative that would be positive, okay? So we are looking for, and again, I'm going to jot this here, concave up would be when f prime is increasing. So let's see, where is f prime increasing? That would be this chunk of the graph here. This is where we're heading uphill, okay? So to answer that question, I would say on the interval from 0 to 2 because, now notice I'm not going to say f double prime is positive. The reason I'm not going to say that is because I'm not looking at f double prime. I don't actually know anything about f double prime. I mean, I do, but I want to talk about what's in front of my face. And what's in front of my face is f prime. So I would say f prime is increasing. Okay, the next question gets a little complicated because we have to think about the first derivative and the second derivative, but only looking at the first derivative graph. So when are we concave down? Well, kind of like what we talked about here. Concave down is going to be when f prime is decreasing. And then when would f be increasing? Well, that would be anytime its derivative is positive. So I need a portion of the graph that is positive, but also decreasing. Okay, running out of colors here. Decreasing, but positive. Well, I see that happening here, but only I'm stopping at that 0 there because then I'm not positive anymore. And I also see that here. Okay, so my answer to that question would be the interval from -2 to -1, and then also the interval from +2 to +5. Justification is basically this, because f prime is decreasing and positive. Okay, one last question, and I'm regretting all the scribbles on my graph, but I think we can make it work. Okay, this question is probably enough to send you into a panic, right? This looks terrifying, and I agree with you. This is a very clever way to test what you know about lots of different things, including the stuff that we're talking about right now, okay? But this is also going to test, first of all, it's going to test your perseverance, right? Are you willing to tackle this problem, or are you going to run away scared, okay? Don't run away scared. You've got this. It tests, do you understand how limits work? It's going to test, do you know how first and second derivatives work? It's sort of going to test your trig knowledge, although we can get around that if we need to, okay? Sometimes you're going to get one of these that ends up being a L'Hopital type situation where you have an indeterminate, and then it's testing, do you know how to use L'Hopital, right? It's putting all of those things in one question, but it's honestly not that hard, okay? Let me show you what I mean by that. First, do we know how limits work? Well, the easiest way to work with limits is just to plug the number in, right? So I would say that this is really equal to 10 to the first power minus 3 times f double prime of 1 over f prime of 1 minus arc tan of 1. Okay, that's all we're doing. We're just plugging the 1 in there. And then, realistically, like the only math we have to do is what is f double prime of 1 and what is f prime of 1. Okay, now f prime, that's the graph that we have in front of us. So f prime of 1 we can read right off the graph. This is where all my scribbles are going to come back to haunt me. But f prime of 1 is just what is the function value right at 1? And that answer is 1. So f prime of 1 is 1. Okay. Now, if I'm looking at the first derivative graph, what is the second derivative? If I were to give you this graph and ask you questions about the derivative of this graph, that would be the slope on this graph. And so if I'm at this x equals 1 and I need to know the slope, conveniently, this is on a nice straight line, right? And so really what I need to know is what is the slope of this line? And this is up 2 over 1. Up 2 over 1. So the slope where this 1 is, this whole section here would just be 2 over 1, or 2. So f double prime of 1 is 2. That's the only real math that's involved here. Now, arctan of 1, you could get away with leaving your answer with arctan of 1 in it. Like, for example, what I have here with these things that are crossed out and written in orange, that's a numerical answer. I could walk away from that right there. In a multiple choice situation, you might have to know what arctan of 1 is. And that's just asking you what angle has a tangent of 1. You know that. I swear you know that. But 10 minus 6 is 4 up top. And on the bottom, we have 1 minus. Arctan of 1 is pi over 4. Because the tangent of pi over 4 is equal to 1. Okay, so that's, and that's just a unit circle thing, right? So, I mean, there's maybe some simplifying we could do here, but this is what I would expect to see in like a multiple choice setting. But again, you could get away with leaving arctan of 1 in there. You would have to have the 2 and the 1 filled in so that it's numerical. Okay, but that's all there was to that one. Okay, I'm going to do, there is one more example here, but honestly, this is probably enough for you to get going on homework. I'll make a video of the next example just so you have it to refer to later. But that should be enough to get you through what you need.